good evening. Let's begin our discussion. If you recall, we are in the world of Fourier transforms and in the world of discrete time aperiodic signals. So, if you recall, we were discussing DTFT, and just to recall few things, let us begin with an example of DTFT. The previous example that we looked at was the DTFT of discrete time impulse, also known as a Kronecker. And as we know, the energy spectral density of this impulse is spread uniformly across all frequencies. The way you should look at it is not just as a mathematical transformation, but some more imagination will help you appreciate this example better. What this example tells us is that it takes all sinusoids, that is sinusoids, when I say sine also imagine cosines, it takes sinusoids of all frequencies to generate this impulse. Now, I should point out, although we are showing the signal on the left hand side and the spectral density on the right hand side, as you know, the Fourier transform itself turns out to be 1 at all frequencies. What this tells us is, to generate this discrete time impulse, one has to really include all the sinusoids. Now, that is fine, I mean it is a mathematical transformation, but if you look at it, what is this that is actually happening? I mean, does it make sense if you look at the signal, right? So, if you look at the signal on the left, truly speaking, there is nothing happening at any non-zero time instance. The only activity is seen is at time 0, right? Whereas what the Fourier transform is suggesting is that you have sine waves contributing, that is across all frequencies, and they are adding up and cancelling out in a particular way, so as to produce this impulse. And what I am trying to point out here is, the signal itself in some sense is not active. I do not want to use the word non-existent, but you can use that. It is not active at all at non-zero times, whereas a Fourier transform seems to suggest that at those times there were these sine waves that were adding and cancelling out each other to produce 0. Now, when you look at the Fourier transform physically, from a physical viewpoint, it does not make much sense. On one hand, we are saying there is no signal activity at all, and on the other hand, the Fourier transform seems to say no, there is no activity because there are people who are screaming and there are people who are shutting the mouths of the people who are screaming, right. It is like trying to express 0 as 1 minus 1, 2 minus 2, 3 minus 3 and so on. And why is this happening? Any idea? Why is this? Isn't this actually kind of a spurious thing? Because on one hand, I know the signal is 0 valued at non-zero lags, on the other hand, Fourier transform seems to suggest that no, there are these mini signals that are fighting against each other and the net effect is 0. That comes from an imagination, right. And at this point, one is compelled to ask, is this imagination justified? But before we answer that question, fundamentally, why is it that the Fourier transform is suggesting that during the the 0 valued instants, which are essentially at non-zero instants, that there are in fact signals adding and cancelling out each other? Why is this happening? Any idea? Why do we see with this kind of a result that is coming out of Fourier transform? You can explain mathematically, but I would like you to look at it from a different angle as well, from the angle of the building blocks that we are using. What are we imagining any signal to be made up of in the Fourier world? Sines and cosines, right. What is the nature of the sines and cosines in terms of their existence over time? They exist forever, right. Whereas the signal under consideration here, it does not exist forever. It only exists for a finite time. It could be a single instant, or in the next example, if you see, this is a pulse. I will show you the pulse. So, on the left hand side you have the finite duration pulse. Even here the signal exists only for a finite time and the rest of the time it is sleeping. Here also if you look at the energy spectral density, it suggests that, or even if you look at the mathematical expression, it suggests that all frequencies are contributing, albeit not uniformly, unlike in the previous case. Here the contributions of frequencies in the low frequencies are more as compared to high frequencies, all right. But the fact remains common in both examples that all the sine waves are participating in explaining a signal, and we know that the signal in time is active only for a finite duration. So, that is a disparity. So, the point now you should observe is the sine waves, which are our building blocks, exist forever, whereas the signal that I am trying to synthesize does not exist forever. It exists for a short period of time, for a finite amount of time, and then thereafter goes to 0. So, here is where one questions the appropriateness of using these kind of building blocks for such signals. It straight away tells us that this may not be the best way to break up a signal of this kind. In other words, you want the building blocks to be commensurate with the features of the signal, and the feature of the signal here is not really commensurate with the feature of the building blocks. So, do I still go ahead and use the Fourier analysis for such signals? Yes, not primarily for detecting the features of the signal per se, but mostly in these kinds of cases we use Fourier analysis for understanding the systems that generate this. That is, there may be a system which has an input and it is producing this kind of an output. In such cases, that is when you are dealing with signals like this, it is perhaps more appropriate to use the Fourier analysis for the understanding of the systems rather than signals. When it comes to periodic signals, maybe Fourier analysis is really good. That is one way of looking, that's one important point, that on one hand we use Fourier analysis for analyzing signals, and on the other hand there exists this huge set of applications where we use Fourier transforms for analyzing systems, their characteristics, filtering nature and so on. The other way of putting it, if you were to be reading the time frequency literature, is that Fourier analysis is not ideally suited to figure out what frequencies are present at what times. So, for example, if you look at the signal or even the previous example, one of the things that you can actually answer is what frequencies have contributed, but if I want to know what frequencies have contributed over what time interval, there is no such information here, at least in the spectral density. You may argue that the phase information contains that, but if you look at the spectral density, the only information that it gives you is what is a contribution of a frequency component to the overall energy. It does not tell you when a particular frequency component was present or what time interval, and that is the limitation of working with spectral densities. That limitation will not hit us in this course. When we go into an advanced time kind of a time frequency analysis course, joint time frequency analysis course, then the limitation does hit us, where we turn to tools like wavelet transforms and so on. So, just to give you some overview. So, now let us proceed and now understand how DTFT is useful in analyzing systems, not just signals. But before we do that, we go through this standard result that we have learnt earlier as well for the discrete time periodic case, where we did, although we did not prove it, and I asked you to just prove it by yourself, fairly easy proof, that the energy there, it was a power spectrum and the autocovariance function. Here it is energy spectral density, we can think of a density here, and the autocovariance function, they both form a Fourier pair. Once again, the only difference is in the periodic signal case, the autocovariance function was periodic and we could think of a power spectrum, and they formed a Fourier pair very much like how a periodic signal and its Fourier series form a pair. Here the autocovariance function is not periodic because the signal itself is not periodic, and we are looking at energy spectral densities. They form a Fourier pair exactly in the way the signal and its Fourier transform form a Fourier pair. Now, pretty much like what we saw earlier, autocovariance function for the random signals satisfies the same difference equation as that of the signal in the autoregressive case. Here also you can say the autocovariance function and the energy spectral density form a Fourier pair. So, there are two ways of computing energy spectral density or even the power spectrum. Let us look at the energy spectral density. One way is to compute the Fourier transform of the signal, right, and then construct your spectral density using this expression. So, if you are given the signal, you can compute the discrete time Fourier transform and then either use if you are looking at energy density in cyclic frequency, simply use mod x of f whole square, or angular frequency just scale it by 2 pi and arrive at the energy spectral density. That is one route. The other route is to construct the autocovariance function and then simply use a Fourier transform. That route is particularly attractive, as we will learn later on, because for random signals the Fourier transform does not exist. Any idea why? Why can't we think of a Fourier transform for random signals? It won't be. What do you mean we don't know? For the Fourier transform. What kind of convergence? Absolute convergence. Are random signals absolutely convergent? They are not, because they exist forever. Any signal that exists forever, right, and does not decay, when we say exists forever, it should not go to 0 asymptotically at all. For such signals, obviously you can't expect absolute convergence. So, for random signals I cannot think of a discrete time Fourier transform. Therefore, I should ask if I can think of a spectral density at all, right. We know already that random signals are not energy signals, we know they are power signals. So, I would like to think of a power spectral density, but unfortunately I do not know how to construct it. It turns out later on, as we shall learn, the Wiener-Khinchin theorem allows us to compute, although it is not a definition per se, but it allows us to compute the power spectral density given the autocovariance function. So, the root of the method of arriving at spectral densities from autocovariance functions is in some sense unifying for both deterministic and random world. That is a very important point to remember. All right. Now, let us move on to the analysis of systems using discrete time Fourier transforms. We will not go much in detail. Typically, this is dealt with a lot more in detail in a proper course on linear systems theory. In linear systems theory, you would actually define what is known as a frequency response function and so on. Here also we will come across shortly, but first let us begin with any two signals. Like we define cross covariance function for any pair of signals. Here, if I have a pair of signals x1 and x2 that are finite energy signals, then I can define a cross spectral density, cross energy spectral density as x1 times f times x2 star of f, or vice versa. In fact, depending on the order here, if you are looking at S x2 x1 as you see on the slide, the cross energy spectral density is simply defined as a product of the Fourier transform of the first signal times the conjugate of the second, depending what is first and second. But the order here matters, which means if I swap the order here, the expression is changed accordingly. You would have x1 of f times x2 star of f, right. This is how the cross energy spectral density is defined, and you can immediately check if I set x2 equals x1, that means if I am looking at the same signal, then what do I recover? It specializes to your auto energy spectral density that we have been studying, right. Now, it turns out that this cross energy spectral density is nothing but the Fourier transform of the, what do you expect it to be? Cross covariance function, right. It is an extension of the previous result, but we will come to that result a bit later. We will study a more important result which is used in the analysis of linear time invariant systems, and this result says if there is a system which is being driven by a signal, we are looking at deterministic systems. So, there is a system G that is being driven by x1 and is generating x2. In other words, x1 is the input and x2 is the output, that is the imagination you can give. And think of this G as an LTI system, it has a transfer function operator representation. We already know almost all linear time invariant systems are described by the convolution equation, right. What do we mean by that? The output x2 can be written as the convolution of x1 with the input. Do not get confused with this n and the n that we have been using in the power spectrum, it is a dummy variable, right. And in symbolic form we write this to be convolution of the impulse response with the input. This star is a special one, it is not your product, regular product, it stands for convolution. Now, the result is that first of all, as we will learn also later on, the Fourier transforms of the output and input are related in a very nice fashion, and that is the beauty of working in frequency domain. So, you can see that x2 and x1 in time are related through convolution. The moment you study the relation in the frequency domain, you can show that x2f is nothing but g of f times x1 of f. What is x2 of f? It is a discrete time Fourier transform of x2, and likewise x1 is of f is the discrete time Fourier transform of the time input. G of f is called the frequency response function. We know now already that there is a name to this small g. What is that? Impulse response sequence. Why is it called impulse response sequence? Because it tells me it is exactly the response that the system will produce to an impulse input. What about g of f? Why is it called frequency response function? Because of this very important reason that if I look at the magnitude and the phase of g of f, it tells me when I excite the system with a sinusoid of frequency f, pure sine, mod g, the first result is, assuming the system is stable, the output is also going to be a sinusoid when after the transients have settled down. The output is also going to be a sinusoid of the same frequency. That is the beauty of a linear time invariant system. It is a trademark characteristic of an LTA system. All of this is useful to us later on when we move to the random signal world. So, if I feed in a sine wave here, out comes a sine wave of the same frequency, but of a different amplitude and phase, otherwise the frequency remains the same, right. In other words, if x1 of k is some a sine 2 pi f k, out comes here b sine 2 pi f k plus phi, and b over a is given by the magnitude, that is called the magnitude ratio or amplitude ratio, and phi is given by the argument of g. Remember, your g of f is a complex valued number. So, by looking at the magnitude of g of f, I can actually comment on whether the system is amplifying or attenuating the sine wave. Why do you think all of this is useful? Do you think, can you think of any application where this kind of analysis is useful? How do I care what an LTI system does to a sine wave? So, what do you mean by filter? So, name at least one application where you think this is useful. All communication devices that we are looking at, right? You tune into a radio station, they are characterized by frequencies. Any remotes, they are in a certain operating in a certain frequency band. You have 2G, 3G, 4G and all of those, right. So, what is this 2G, 3G and all? They are all corresponding to some frequency bands, and your devices that you are using, cell phones and so on, they all have certain filters that are tuned to receive frequencies only in certain frequency bands. So, whether you like it or not, this finds extensive applications in all the technology that we use today. Essentially, that is in technology. In signal analysis, it is used in designing filters. The actual signal may not be a sine wave. That is one thing that you should remember. In reality, the true signal that is exciting the system may not be sine wave, but Fourier analysis allows us to imagine that signal that is coming in to be made up of different sine waves, and g of f tells me how the system treats each of those elementary sine waves that are making up the signal. And because of linearity, I can think of the output signal being again resynthesized only after the signal the system has altered the amplitude and the phase of the individual components of the signal. So, the truth may be that the signal is not a sine wave, but we are imagining the real input to be made up of many sine waves, and that the system is actually responding to each of those sine waves based on g of f, and then at the output side there is a resynthesis. All of this is imagination, but this imagination has helped us enormously. That is the point, and that is, if you appreciate that, then you will have a better and grander respect for Fourier analysis. Okay. So, this this is the first result, that is x2 of f is g of f times x1 of f, but a more useful result is in terms of spectral densities. Why do I keep saying this? Because when we move to the random signal world, I would, first of all, we have already said this, Fourier transforms of random signals do not exist, but spectral densities may exist. We have not yet talked about it, but spectral densities can be thought of. And therefore, I would like to have a result that tells me how the spectral densities are changed by the system rather than the Fourier transform. So, the first result says that the cross energy spectral density, here we are talking of energy spectral densities, it says the cross energy spectral density is nothing but the auto energy spectral density of the input multiplied by g of f. I have written g of f on the board, but on the slide you have the more correct one, g of e to the minus j 2 pi f. How does one obtain g of f? By the way, I have not given the definition here, but by now you know, I suppose it is nothing but the Fourier transform of the, I have reached my limit. Okay. So, it is a discrete time Fourier transform, let me put it this way. Of the impulse response sequence. So, everywhere the DTFT is coming handy. Now, you see, more than the signal analysis part, the DTFT is useful in describing the system's behavior, right. And this should tell you, we already know DTFT of any sequence exists only if that sequence has an important property, which is that the sequence should be absolutely convergent. what does it tell us about the kind of systems for which I can think of G of f? Its impulse response should be absolutely convergent, correct? What does it tell us about the nature of the system? Deterministic world stable, random world stationarity, we will come to, correct, good, very good. So, only for stable systems you can think of a frequency response function. Why? Because we have, go back to what I said earlier, I said LTI systems have a trademark characteristic, which is if I feed in a sine wave and you allow the transients to die down, you will see the sine wave of same frequency. But when do the transients die down? Only if it is stable, correct? So, all of it is interconnected, everything is consistent here. So, you should think and speak of frequency response functions only for systems that are stable in the deterministic world. So, now the result on the screen says that the cross energy spectral density is the frequency response function times the auto spectral density of the input, that is how it is shaped. You should check that everything is consistent on both sides. What I mean by that is, on the right hand side you have a product of G of f times the auto energy spectral density, we are looking at the left bottom relation. The auto energy spectral density, is it real valued or complex valued? Real valued, right, because it is a squared magnitude squared quantity. What about G of f? It is complex valued. So, we know already that the cross energy spectral density in general is complex valued. So, things make sense. On the other hand, you look at the second result, there is a G1, do not worry about G1 there, that is, it should not have appeared there. Anyway, so the auto energy spectral density of the output, that is, the second result tells me how to compute the energy spectral density of x2 given the energy spectral density here of the input and the frequency response function. What does this tell me? How to, what is the Fourier transform of x2 given the Fourier transform of x1 and G of f? But now the result tells me how to compute the energy spectral density of the output given the energy spectral density of the input and G of f. Why is it useful? It is useful because now this result will tell me what the system is doing to the input, right, because the energy spectral density of the input is being shaped by magnitude square of the frequency response function. Look at the difference in the two relations that we have at the bottom. On the left hand side, the relation tells me how the cross energy spectral density is shaped by the system, and on the right hand side how the energy spectral density of the output is shaped by the system, and in both cases the frequency response function plays a critical role. But the only difference is, in the second case only the magnitude square is responsible for the energy spectral density, the phase has no role to play. Okay. So, therefore, this magnitude square of the frequency response function is a very important thing that we want to look at. In fact, when we move to the world of random signals, we will see a similar result, where what do you expect x1 to be replaced by? White noise, very good, right, and x2 would be the stationary process under consideration, and G would be replaced by H, right. So, and there is one more difference, which is the energy spectral density being replaced by power spectral density. So, this is all a curtain raiser for you, so that you are not in for some surprise later on. I am kind of developing the connections now itself. Okay. So, you can think of this as your home and that as your in-laws place, the random world. Okay. I am just showing you what you are going to experience there. Fine.